In this video, we're going to look at an introduction to the reciprocal and inverse trig functions. So just an easy way of remembering what these are, if we were asked about sec theta, if you look at the third letter, it's a c, so that would be the same as 1 over cos theta. Cosec, 1 over sine. Cot, 1 over tan. The third letter tells us each time. Notice that this last one is 1 over tan, but it's probably for most of the questions involving identities easier to think about it as cos theta over sine theta. Just one thing to be really careful of, sine inverse is what we call arc sine, but sine inverse is not the same as cosec. Okay, cosec is just 1 over sine, it's not sine inverse, so that don't get these two things confused. Alright, so we're going to look at how to sketch these different trig functions, the reciprocal functions. So let's start with cosec. Okay, and obviously you can do this on your graphical calculator, but it's good to have an understanding of where this graph comes from, because it will help with other things later on in the course. So all we need to really do to think about what this graph is going to look like is just to know what happens when you divide 1 by something. Okay, so just think about this for a second, like, what's 1 divided by 1? What's 1 divided by minus 1? And what's 1 divided by 0? And like, I could basically draw the graph just from understanding those three things. Obviously 1 divided by 1 is 1. Okay, 1 divided by minus 1 is still minus 1. And this is undefined, isn't it? So when something's undefined, think about it, right? If you divide 1 by something really small, so if I divide 1 by 0.0000, if I divided 1 by something really small, the answer would be really big. So as we get closer and closer to 0, the answer is going to be, well, it's going to tend towards infinity. Okay, I'll write equals infinity, it doesn't equal infinity, but when we divide by something really small, it gets really large. Okay, because how many times does 0 go into 1? Well, as many times as you want. Okay, so that you might be thinking, what am I going on about here? Let's just look at the graph. Okay, so the graph that I've drawn is the graph for sine x. Okay, so let's say if I wanted to work out when x was equal to pi over 2, y would equal cosec of pi over 2. Now there isn't a button on your calculator to work out what this is, so instead if we're working with cosec, we just write it as 1 over sine of pi over 2. And then if you worked out sine of pi over 2, the answer we'd get would be 1. So what's 1 divided by 1? That's still 1, isn't it? Okay, so what this is telling us, if I sub pi over 2 into cosec, it's 1 over sine of pi over 2, which is 1 over 1. So the answer is still 1. Okay, I'm not going to do the whole process again, but think about with 3 pi over 2. So if I wanted to work out cosec of 3 pi over 2, then that would be the same as 1 over, what's sine of 3 pi over 2? Well, that's 1 over minus 1. So we get minus 1 again. So these 2 points are when sine and cosec are the same. Okay. The next one to think about is what happens at these points here. Okay. So if I was going to work out cosec of pi, that would be the same as 1 over sine of pi. Now sine of pi is 0, so it's like when you're trying to calculate 1 divided by 0. And essentially what happens at this point is it's undefined, isn't it? You don't actually get a value, and graphically what that means is that because we can't sub pi over 2 into this function, because it's the same as doing 1 divided by 0, pi, we can't sub pi into this function, we get a vertical asymptote. Remember it from rational functions, like 1 over x, you get an asymptote whenever you divide by 0, don't you? So whenever sine is 0, we get these asymptotes, because you're trying to do 1 divided by 0, essentially. Okay, And then you can sort of fill in the gaps, but maybe let's think a little bit more about it. So if you look at the graph, right, as sine gets smaller, what happens when you're doing 1 divided by something small? So as the sine value gets smaller, cosec is 1 divided by something small, which is going to be big. So as the sine graph approaches 0, our new graph approaches this asymptote. I'm going to have to be careful as I draw this. You get, as you draw it, make sure it just gets close to that line but never touches it. Apologies for the terrible sketch. It's not easy on this whiteboard. And then similar for over here, right? As it's negative but small, so 1 divided by minus small would be minus big, wouldn't it? So as this gets closer to 0, our graph gets closer to infinity. Okay. So this is what the shape for cosec looks like. It's basically a sequence of u's and n's. It just would repeat periodically every 2 pi, just like the sine graph repeats. I would recommend that you remember what these graphs look like, but it's useful to know the knowledge of where they come from as well. Okay, maybe pause and try and figure out what sec would look like, because that's 1 divided by cos. You could draw it using the same skills that we've just used for this one. Okay, so for the next one, we've got sec, which is 1 divided by cos. So I've drawn the graph for cos. So if I subbed in 0, sec of 0 is 1 over cos of 0. Cos of 0 is 1, so that's 1 over 1, which is 1. So when I sub 0 into my sec function, the answer that I get is 1. If I sub pi in, it's 1 divided by minus 1, so I'd get minus 1. If I subbed pi over 2 in, it would be 1 divided by cos of pi over 2, which is 1 divided by 0. If I sub 3 pi over 2 in, it would be 1 divided by 0. So this is where my asymptotes are going to be. Okay, and then we can just fill in between the point that we know exists and the asymptotes. As that gets smaller, 1 divided by small gets big. Apologies for the sketch. So you get this sort of shape. It's very important that when you draw this, right, don't do that. Like, if you drew it going vertical, you would lose a mark in the exam. Like, it clearly needs to approach this asymptote but never touch it. Okay, same for here. Approaches this line. And obviously if the domain was more than between 0 and 2 pi, if we were going to draw it that way, it'd be going up that way as well. We've got this point as well, so when we sub 2 pi in, cos is 1, so we get 1 divided by 1, which is 1 again. So we've got this section. Okay, in the exam it might say sketch between 0 and 2 pi, for example. Like, it will always give you an interval to do the sketch for, because obviously otherwise it would just carry on with using ends forever. Be very careful. If you just plug this in your graphical calculator, the calculator will just draw this, like, loads of u's and ends. Like, it's so annoying when people just go, yeah, there's the sketch, there's loads of u's and loads of ends. Like, that is not going to get you the marks in the exam. Like, you need to clearly sketch it between 0 and 2 pi if you're asked to do so. You need to show the asymptotes, label the asymptotes. You need to show that we get this value at 1, this value at 2 pi, we get 1, minus 1 when we sub pi in. So you don't need to draw the cos graph if you're asked to sketch sec. I just drew that for reference so we can see where it comes from. Okay, so the last reciprocal function is cot, which is 1 over tan. Bit of a slightly different way of thinking about this one, but again, I've started by drawing the graph for tan, and then all we have to do is think about, well, if these are my answers here, what's 1 divided by the answer going to look like? I'm going to ask you this question: what's 1 divided by infinity? And again, we've got to be careful with infinity, but I suppose if we think about it, if we do 1 divided by something really big, the answer's going to be really small, isn't it? So what we could think about is, for this question, 1 divided by infinity could be 0. So can you see, as this graph, as tan gets really big, right? If you try and do tan of pi over 2, you're going to get a math error. So like if you do tan pi over 2 on your calculator, you can't sub pi over 2 into tan because it basically approaches infinity. So as this graph approaches infinity, cos is going to be 1 divided by something really big, which is going to be 0. So where the original asymptotes were for tan, they're going to be roots for cos. So that's going to give us a root. That's going to give us a root. That's going to give us a root. Another maybe slightly easier way to think about it, right, is cos is the same as cos x over sine x. So if I did cos of pi over 2 divided by sine of pi over 2, cos of pi over 2 is 0 divided by 1. So we can see that cos of pi over 2 is the same as this divided by this, which is clearly just 0. So if I sub pi over 2 into cos, I'm going to get 0. Okay. Then we get a slightly more familiar one. If we sub pi in, so we do 1 divided by tan of pi, which is 1 divided by tan of pi is 0. So we're trying to do 1 divided by 0. So that's where our new asymptotes are going to be. Same here, we're going to get a new asymptote. And any others? No, that's it for the sketch. Okay, so we know where tan was 0, that's where cot gets an asymptote, and we know where tan had an asymptote, that's where cot is 0. Okay, and then when it's positive, clearly it's still going to be positive. They actually intersect. I'm going to have to be careful how to draw this. The point where they intersect here would be a y value of 1, because again you'd be doing 1 divided by 1. Okay. And that would actually happen at pi over 4. You don't need to show that on your sketch, it's just for a bit of extra knowledge. Just think about the symmetry of it as well. It intersects at the midpoint, so at pi over 4, that's when we get tan of pi over 4, which is 1. So the intersection point would be at pi over 4. Then we pass through pi over 2, and then the asymptote is a pi. So we bend down this way. And again, it would intersect at that point there, which would be -1. And that would happen at 3 pi over 4. Okay. And then this one shape would just repeat. And for down here, we get it this way. Again, if you are asked to sketch this in the exam, please don't do all this stuff. Just draw the blue lines and make sure you label your asymptotes and the points where it intersects the axis. Okay, next let's look at how to sketch the inverse trig functions. Before we do this, I'm just going to do a little recap on some of the properties of functions and inverse functions, because it's really important that we know that. Okay, so let's just start with a simple graph, x squared, right? And I'm going to use f of x actually. So f of x equals x squared. So what's the inverse? What's the inverse of x squared? You know, what's the opposite of x squared? And you might think, well, that's the square root, isn't it? That's the opposite of squaring is the square root. But what we've got to be really careful of is think about what an inverse function does, right? If I did f of the inverse, that should always take me back to the original input. Like when you apply a function and it's inverse, whatever you put in, it takes you back to what you started. So for example, if I said, if I was subbing 2 in, well, the square root squared would be 2, so that would still work, wouldn't it? Like the number that you put in, it'd take you back to the number that you put in when you do the inverse and the function. Why am I going on about this? Like, look at the graph, right? So say for example I subbed 2 in, so my input was 2. My output would be 4, wouldn't it? So that's when you apply the original function. You go this way. Sub in your input, get your output. Okay. Now what an inverse function does is it tries to go the other way. So it takes the output and it takes you back to where you started. Okay. So if I said, well, here's my answer for how do I get back to where I started? You'd think, well, I go back to 2, which would be fine. But what happens if my input was -2? So if I put -2 in, my input would be -2, my output would be 4. So when I'm stuck at this output, how do I know which way to go back? Do I go back to the -2 or do I go back to the 2? Okay, and the problem with this essentially is the function is not 1, 2, 1. And that's a key term that we need to know. Like, if you want to find an inverse of a function, first of all, we need to restrict the domain so that it's 1 to 1. Like, we can't get this situation where 2 inputs give you the same output. The easiest way to think about it is if you draw a line across, if it crosses the graph twice, that function is not 1 to 1. So we can't find the inverse for that function yet. Okay. What we have to do is we have to restrict the domain, and very often in a question they'll give you the domain. So let's say x is greater than 0. Now if x was greater than 0, we'd only be working with that part of the graph, wouldn't we? And that means you put one number in, you get one number out. And the function's 1 to 1, so you can easily figure out what your input was and then go back to where you started. So this, we would be able to find the inverse of, okay? And which would be the square root, it'd be the positive square root, wouldn't it? Okay? So with that in mind, let's look at the trig functions. So the first one we're going to look at is arcsine, or sine inverse, okay? Now let's just start by looking at the sine graph, okay? Now if I was going to find the inverse function for sine, clearly it's not 1 to 1, like the original graph is clearly not 1 to 1, like that graph would just repeat, wouldn't it? And like, if you drew a line across, there'd be loads of different inputs that gave you the same output. So before we can find the inverse, we have to restrict the domain, and the way that we do it is we go from pi over 2 to minus pi over 2. Because if we go from pi over 2 to minus pi over 2, look at what section of the graph that we get. We get every possible answer from -1 all the way up to +1. So this little section here, this little window, is a section of the graph that is 1 to 1. So we put one number in, we get one answer out, and it gives us all the possible answers as well. So that's why we choose this section. Okay, so the original domain would be between minus pi over 2 and pi over 2, and the original range would be, the function would be between -1 and 1. Remember, the domain is the numbers that we put in, the range is the answers that we get out. So you can see the range for this question, clearly we get every answer between -1 and 1. So that's our range here. Okay. When you're sketching inverse functions, all you need to remember is think about how you would find an inverse function. Like the first key step to find an inverse function is you swap the x and the y around. So that's all we really need to remember. That coordinate there would be, the original coordinate would be pi over 2, 1. And that coordinate there would be minus pi over 2, minus 1. So the inverse function that we're about to sketch, instead of being pi over 2, 1, would be 1 pi over 2. And instead of being minus pi over 2 minus 1, it would be minus 1 minus pi over 2. Because for the inverse function, remember that the domain and the range swap around. So we actually, before we sketch it, let's think about what the new domain and the new range would be. Okay, so another property that we should know about functions, for the inverse, the domain and the range swap around. So the original domain was between minus pi over 2 and pi over 2, that's the x values. Our new domain, remember, we have to always use x for the domain, would be the range for the original one. So the x values now are going to go between -1 and 1. Which makes sense because we knew that coordinate now is -1. That's our x coordinates. So our x values go between -1 and 1. The range, again, this is going to be the function. I should write the correct definition, which is the inverse function. So the range is telling me about the y values that we get out. If you look at your graph, the answers now go between -π/2 and +π/2. And also, let's just check, the range for the inverse should be the same as the domain for the original. Okay. Last thing is to think about the curvature. It doesn't look like this, the sine graph. Okay. And the reason why is when you find an inverse function, geometrically, you reflect it in the line y equals x. So the curvature actually goes the other way now. So the inverse function, oops. Looks a bit like tan. It is not tan. Like there's no asymptotes on this, so just when you draw it, don't get it confused with tan. Like there's a definite stopping point. It stops there, and then this one stops there as well. Okay, so if you are asked to sketch this, label the key points. So 1π/2, -1 -π/2. It goes through the origin. Maybe pause and try and do the cos inverse one before I show you what that one looks like. Okay, so similar process for arc cos or cos inverse. If you look at the cos graph, clearly that would just repeat, would not be 1-to-1. So we have to restrict the domain so that we get a section of the graph that's 1-to-1. Now we can't use -π/2 to π/2. That wouldn't work, would it? Like if you use -π/2 to π/2, you would get a section that is not 1-to-1. So we use 0 to pi. Okay, so if we go from 0 to pi, we get a section of the graph that's 1-to-1, and also we get the full section of answers that we want. Like we get every answer from -1, from 1 to -1, don't we? Okay, so the domain for this original cos graph is, we have to restrict it to be between 0 and pi. And the range is the same. We get answers between -1 and 1. So let's quickly use that to help us with our inverse graph that we're about to draw. So remember, the domain and range swap around. Okay, so the domain was between 0 and pi. That means the range is going to be between 0 and pi. The range was between -1 and 1. So that means the domain is going to be between -1 and 1. Remember that we're just when we find an inverse function, geometrically we're reflecting in y equals x, we're swapping the x and y coordinates. So it might be useful if we look at a couple of coordinates on this graph and then use these coordinates to help us with the new graph. That coordinate there would be pi -1. That coordinate there would be pi/2, 0, and that coordinate there would be 0, 1. So let's start with 0, 1. That means my new coordinate is going to be 1, 0, because we swap x and y around. If it crossed the x-axis at pi/2, now it'll cross the y-axis, because that coordinate there would become 0, pi/2. And if it used to be pi -1, now it would be -1. And it would be up at pi. So that coordinate there would be -1 pi. Okay, and again, as we reflect this, imagine the line y equals x. It's quite difficult to visualize this, but imagine if we had the line y equals x. This section of the graph is being reflected in that line. Okay, so we end up with the curvature going this way. And that's what the graph for cos inverse looks like, or arc cos. Okay, last one. We've got tan, and we're going to draw tan inverse, or arc tan. I've only drawn one section of the tan graph, because clearly that there is the section where it's 1-to-1. If I drew this shape again, it wouldn't be 1-to-1 anymore. So the domain that we restrict for this one is between minus pi over 2 and pi over 2. Okay, so if we restrict these x values, now be careful here. It's not allowed to equal pi over 2 because that's when the function's undefined. So it's actually less than pi over 2 and greater than minus pi over 2. Okay, and the answers that we get out, well, if you think about the graph, it's approaching this asymptote, isn't it? As we get closer and closer to pi over 2, the graph gets larger and larger and larger. So there isn't actually a restriction on this range. Like we can get any answer we want as high up as we want. We can get any answer we want as far down as we want. So we could just say that f of x is an element of the real numbers. That basically means that the answers that we get out, we can get any number out that we want, any real value. Okay. So let's translate over here. The domain would be x. The range for the original is the domain for the inverse. So we can say, well, x could be any real value. So what that straight away is telling me is that this graph is going to be defined for all x values. Like I can sub any x value in I want. Okay. The range would be the inverse function. And that's the same as the domain for the original. So it's going to be greater than minus pi over 2 and less than pi over 2. Okay. So the answers that I'm going to get out, the biggest answer, well actually the answers will approach pi over 2 and minus pi over 2. So we get these answers out in between. Okay, and then the last thing is think about swapping or reflecting in the line y equals x. Okay, so the vertical asymptotes now become horizontal asymptotes when we reflect in y equals x, or when we swap the x's and the y's around. And the graph used to go like this. If you reflect it in y equals x, it curves the other way and it approaches this asymptote. So the graph ends up having, that's terrible. The graph ends up having that sort of shape. It's not easy to draw on the whiteboard. So you get this sort of shape. Clearly make sure you show that it's approaching the asymptote and that you label your asymptotes. And that's what tan inverse looks like. Okay, thank you.